Pre-calc section 4.7, and yes, we're skipping 4.6 for various reasons. It didn't fit with anything that you really need, and we have so much other stuff to cover. We're not going to get through like half of the book. It's just one of those things where there's a lot of material.
Oh, what isn't? Like what stuff do you do?
Oh, in 4.6?
Yeah.
Oh, just take, flip through there. Because it's one of those things where what we want to do is cover more of the in-depth stuff that you will need when you go to calculus. So we're going to get some pieces of trig here that would be helpful with that. We will be able to understand restricted domains and ranges of inverse trig functions. So if we say we want to use the inverse, what we're doing is we're trying to find the angle that gave us whatever our value is for sine, cosine, and tangent. So we want to work backwards here and figure out how that works when you're trying to work backwards and find the angle. So we're going to evaluate those inverse trig functions, and we're going to compose trig functions and inverse trig functions, but that'll probably be tomorrow. And apply inverse trig functions, yeah, that's in our future, but it's going to take us a little while to get there, because the first thing we need to do is review what on earth is an inverse trig function. What do we use it for? So a quick review of trig functions is inputs and outputs. If we're looking at x is our angle. So we like those angles in radians. That way we can work backwards and figure out what the sine of that is. And sine, remember, is a ratio of two sides of a triangle. And a long time ago, when we first started this, we talked about how sine and cosine will always be between -1 and 1. And that's because they have the hypotenuse for their denominator, and the hypotenuse is the longest side in a right triangle. So when you talk about domain and range, we really could put whatever angle we want in there. However, when we do the sine, we get something between -1 and 1, and that is never more evident than when you look at the graph and you realize, well, we just always go -1 and 1 unless there's an a value to change that. So this ratio, again, spits out something between -1 and 1. And like it says, we've already had a little experience with an inverse trig operation, but what we need to do today is beef it up. We really do. So this says, if the sine of theta is 5/7, we want to figure out what our solutions are between 0 and 360. So right away, I started thinking about the fact that if they're talking about 360, they mean all the way around this fucker. Where is that going to happen? And it is a positive 5/7, and that's a huge clue, by the way. That's telling me first quadrant is an option. Second quadrant is an option, because remember, sine, cosine, and tangent, sine will be positive over here. But third and fourth are out. Can't do that. And that's because these would give me negative values. So now, start thinking, okay, sine, 5/7. Let's see. We have an angle here, and opposite over hypotenuse. And I've got this 5 and this 7 piece. Well, that's not a 30/60. And it's also not a 45/45/90. Well, that happens. There's a lot of angles out there that are not 30/60/90 or 45/45/90, but we still have to find them. And that's where we use the inverses. If we want to undo the sine, what we're asking is, what angle would give us the 5/7? And we're going to be careful to put it in degrees today, because we're going to talk about this in terms of degrees. So make sure we've got our calculators in the degree mode. That means going into the mode and getting that switched out from radians. Some of you might already have it in degrees for other classes anyway. But we want to make sure that that's highlighted. I'll press enter a couple of times when you're on there just to make sure. So now, I know that I need the second function for sine, which is the inverse. That's not reciprocal. It's saying the inverse sine, and that is to get the angle for us. And we want that for 5/7. And we get 45.585 approximately degrees. 45.585 degrees. But I also know that's not the only angle that's going to do that, because if I go in second quadrant, where sine is also positive, I can have the same setup over here. And I'll just put theta 2 on there, because there's a second angle that would give us that. So for that one, we kind of think, okay, I need this angle positioned over here. And I already know that this is 45.585 degrees here. So what I need is, well, to figure out from 180, take that chunk out of there, because that'll give me this terminal side. So I need to take 180 minus my 45.585 degrees in order to get the second solution for this. And in order to keep everything perfect, I'm just going to do 180 minus answer. So 134.415 degrees is what we get. So doing this problem makes me ask myself a question. If you're going from 0 to 360, how many solutions would there be for each of the three primary trig functions? Well, sine had positives here and here. Cosine would have positives here and here. And tangent would have positives here and here. And if we went back with the negatives, we realized, well, that happens too. So between 0 and 2 pi, or 0 and 360, we should always be coming up with two solutions. There should be two for any of these, unless we start restricting the domains. And that's a big piece of what we're going to do today. So we've got this all solved. We found our solutions, and it says, notice that the equation above had two solutions going all the way around 360 degrees within one positive rotation. And if we say find all the solutions, we're going to have to come up with a formula, because that would have infinitely many. And like it says, if we count coterminal angles, multiple rotations, it's infinitely many. So we would come up with a formula to show people how that works. Kind of like we had to do for the vertical asymptotes for cosine and sine. When we went through that, you know, we come up with a formula way to tell people, hey, here's where they're all at. So what it says is, remember that for a function to have an inverse that is also a function, it must be 1 to 1. In fact, we just covered this last week in Algebra 2. To be 1 to 1 is special, because what it means is, not only was your original function a function, but when you found its inverse, that was a function as well. And a lot of math can be done when you have functions. Any old relation? No. You know, every once in a while you run into a problem. But if you have a function, that's really special. And to have a function whose inverse is also a function is really, really special. So we want it to be 1 to 1. The 6 basic trig functions, being periodically, fail the horizontal line test rather spectacularly. Yeah, you know, think of our sine and cosine, and you draw that horizontal line. It's hidden infinitely many times. It's not going to pass it. But sine and cosine and tangent are so, so important. We have to be able to use those as 1 to 1 functions. So the way that we do that is by restricting the domain, which means we're not taking the whole graph. We're not taking that wave forever. We're saying, let's just take a chunk of this graph that would pass the horizontal line test, and we use that information. So like it says, however, since they are so important, we look for a restricted domain where they will be 1 to 1 within that little domain, thus allowing us to work with the inverse functions. So what we want to do is we want to show a 1 to 1 interval. We want to take on all the y values of the trig function. We don't want to leave anything out. We want to show what it's doing, but we want it to be 1 to 1. And it needs to be, of course, convenient. We would love to have it be convenient. So, inverse sine function. Like it says, let's just sketch the graph of the sine of x. Won't hurt us. We've done this a lot. Negative 1 to 1. The period for sine is what? 2 pi. So we split that into 4, and we've got our little pi over 2 pi, 3 pi over 2, and 2 pi, and our negatives. and sine is Sahala. So axis, high, axis, low, axis. But like they said, we draw a horizontal line on this, yeah, it's failing miserably, absolutely failing miserably. So here were the keys to what they said. They said, pick a portion of this graph that represents all of the y values that you will need. So basically what we want to do is just pick from -1 to 1. We don't want anything to repeat. And now if I take off the graph that's not within -1 to 1, that's going to pass the horizontal line test. Because this would be gone, and this would be gone, and yeah, now if I take its inverse, it's going to be a function. So it's looking at the graph and saying, okay, well, what's going to work here? What's going to give me -1 to 1 and show me that horizontal line test will pass? So the interval we're going to choose is -pi/2 to pi/2. That will show all of those y values, and it's convenient. You know, it's small. It's right in there by 0, so it's going to work out pretty good. But now it says sketch the graph of the inverse of that function. And what we have to remember about inverses is the domain becomes the range, and the range becomes the domain. For us, that means the x's become the y's, and the y's become the x's. So before, when we made our intervals, we put a 1 and a -1 here. Well, now we're going to have to reverse that. This is going to be pi/2, and -pi/2. And our y values were going to be -1 to 1. Well, not anymore. If it's an inverse, it's going that way. So we look at our graph up here and we think, okay, so what I have to do is I have to take the points I have up here and turn them around, graph them backwards. This was pi/2, 1. So I have to graph 1 pi/2. And then we look at -pi/2 and we see it's at -1. So that's going to be -1, -pi/2. And we could take a lot of time and find, you know, the points in between there. Well, we wouldn't necessarily need a lot of time. Let's give this a try. If we take a look at what's happening at -1/2, the graph will have an x value here of what looks like it's going to be halfway. That should be if it's going to be symmetric. So we would have -pi/4 and -1/2. So if we flip that, that's going to be -1/2 and -pi/4. And because of symmetry, you kind of do the same thing over here. And the graph just ends up being kind of a little squiggly line here. So we were really careful and went through and got a lot of the points. But that's the inverse that we can use that will be 1 to 1 with sine. And if you wanted to go a little further, you could look at this and say, okay, here's what I know. For 45 degrees here, or not 45, for 30 degrees, this will be the square root of 3/2, 1/2. So we could use the unit circle to get points as well. And then square root of 2/2, square root of 2/2 for 45 degrees. And then 1/2 square root of 3/2. But that unit circle is going to be really helpful to us because what we can see here is we're going to use sine of x from that -pi/2 to pi/2 in order to make this work. In order for us to have a 1-to-1 relationship, that's what we have to be between for our y values. And that means the inverse sine function is defined for just those two quadrants. those two quadrants, because that takes us from 0 to pi over 2 and 0 to negative pi over 2. So whenever we work with inverse sine, we're going to focus our energy on just quadrants 1 and 4. And that, in fact, is called the principal value range. The names make sense if you think about the fact that what we're trying to do is not use the whole graph. We're saying, let's just use a chunk of this graph that will make this inverse 1 to 1, this whole relationship between these two 1 to 1. And that means we're going to have to leave some stuff out. And we're going from negative pi over 2 to pi over 2. Well, that's the right side of this axis, the right side. So there it is. That's the principal value range. So when we're working with inverse sine, our focus is always going to be on getting it into that principal value range so that we can figure out what's going to happen with it. And then, like it says here, this is going to change our domain and range because we've sliced it off. We've said don't use the whole thing. So our domain is now from negative 1 to 1. And our range is that negative pi, principal value range, negative pi over 2 to pi over 2. Because we don't want the whole thing. It's too overwhelming and it's not 1 to 1. So we pick a portion of the graph to make it work. Now, you're going to find as we go through these that there's a principal value range for sine, for cosine, and for tangent. And one of them is different. And one of the things that I've always done that's made it very easy for me to remember the principal value range is just a simple little mnemonic I call opening a door. If I open a door, go to reach for the handle. Everybody reach for the handle. You're opening a door. Now, your hand is just kind of sitting like this because you don't know what kind of handle it is, right? Now look at the shape of my hand. See how it's on that portion of the circle? Right here. Now when I open the door, I turn it. And it'll look like this. That's going to be cosine. Cosine's principal value range will be quadrants 1 and 2. And then I turn it back so I can pull the door open. And that's going to be the same quadrants for tangent. So like I said, it's just a really easy mnemonic device I've always done. I go to reach for the handle. There's my hand. There's quadrants 1 and 4 for sine. Turn the handle, quadrants 1 and 2 for cosine. Back again, and quadrants 1 and 4. And it's just really easy to remember those principal value ranges. Because we have to do all three of these. It's not just sine that we want those 1-to-1 relationships for. We want all of this to work. So the inverse sine function is the function f of x equals inverse sine of x, domain negative 1 to 1, and principal value range. Principal value range. Negative pi over 2 to pi over 2. We restricted the domain, so that changes what our range is. This means that x represents a sine ratio and f of x represents an acute angle in either quadrants 1 or 4, because that's where negative pi over 2 to pi over 2 is in those two quadrants. The inverse sine function, there are some really old textbooks that call it arc sine. So we need to know that they're exactly the same thing. If you see arc sine, that's still inverse sine. It's just kind of an older language that is always used for that. Some people think it's really helpful because the name arc sine, arc kind of gets you thinking about where it's going to be at. And where is that curve that you're going to use for that. So it says it's helpful to think of inverse sine or arc sine as the angle between negative pi over 2 and pi over 2 whose sine is x, because what we're doing with those inverse functions is we're finding an angle. That's our job, find an angle. So we take inverse trig functions of ratios to work our way backwards and find an angle. That's what we do. So down here it says evaluating inverse sine of x without a calculator. And we want to find the exact value of each expression without a calculator. So I look at A, and right away, I'm thinking about where I'm going to locate all of this. And it says my inverse sine has to be for 1/2. And I realize, well, because it's inverse sine, I have to be working in the principal value range. So everything's positive in first quadrant, but that sine is negative in fourth quadrant. And this brings up an interesting point about that principal value range. If you look at this, you'll see that sine is positive here and negative down here. So we have a way to represent a positive sign in first quadrant and a way to represent it in fourth quadrant as a negative. So since that's a positive 1/2, I should go in first quadrant. It was positive. And then sine is opposite over hypotenuse, 1 and 2. And that makes us think of a special triangle. Which one? 30, 60, 90. And if you need to, if it's helpful for you, you put the square root of 3 down here. But really all we needed to know is where this 1 is, because this 1 is always opposite the smallest angle, which is 30 degrees. However, it said find the exact value of each expression without a calculator, and whenever they do that, we always want to give our answer in radians, because radians are exact. So instead of 30 degrees, what are we going to tell them? But we think 30 degrees because we can't. It's just one of those things where we're still kind of translating that in our mind. Okay, let's go on to the next one. Negative square root of 3 over 2. Inverse sine, principal value range, but it's negative this time. Well, for that to work, it's going to have to be down here. Has to be. Because remember, everything's positive for sine in first quadrant, and then everything's negative for sine in fourth quadrant in that principal value range. So this time we've got opposite square root of 3 over hypotenuse 2. Pretty obviously, this was the negative because it's going down. And again, that might be enough for us because we're looking for this angle. What is that angle? 60 degrees. So 60 degrees in terms of radians, pi over 3. However, remember we have to be between pi over 2 and negative pi over 2. And remember, we wrote these so we can have positive answers, so this is we can have negative answers. We're going to slap a negative in front of them. Because when we're dealing with inverse sine, we're staying within that principal value range, and we're just swinging up to get the positive answers and down to get the negative answers. So negative pi over 3. Take a look at C. That looks interesting. Inverse sine of pi over 2. Wait a minute, I think we got a problem. Opposite over hypotenuse. Doesn't that always have to be between negative 1 and 1? Is pi divided by 2 going to be between negative 1 and 1? We can't do this problem. Take pi. Divide it by 2. It's more than 1. It doesn't exist. So this is a trick question. You can't do that one. It does not exist. So while you're doing them, you want to think, okay, wait a minute. This is supposed to be between negative 1 and 1. And at first, you look at it, wait a minute, I've got to do opposite is pi and hypotenuse is 2. I don't know a special triangle that does that. Then there should be bells and whistles going off in your head. Okay, this has to be some kind of trick. There's something weird going on with this one. And you go back and rethink it. All right, let's look at D. D has us looking at the inverse sine of the sine of something. Well, just like inverses work, inverses undo each other. So the answer should be whatever it is you start with, unless that thing that you're starting with is not in the principal value range. If it's in the principal value range, this is a very easy problem, and we put down pi over 9. If it's not in the principal value range, then we have to figure out how to get it there. Is pi over 9 going to be in our principal value range? So the answer to this is just pi over 9. Pi over 9 is going to be pretty small. We already have pi over 6 for 30 degrees, so it's going to be a small angle. But it's definitely in quadrant 1. And since it's in quadrant 1, then these two will just simply undo each other. Inverse sine and sine undo each other. Well, the next one says 5 pi over 6. And notice, it still has inverse sine and sine, but 5 pi over 6, that's over here. That's not in the principal value range. So with this one, we're going to have to think our way through, well, what would be in the principal value range that would give us the same thing as the sine of 5 pi over 6? Well, it's positive. It's got to be in quadrant 1. So this angle needs to be the same angle as that. What reference angle in the red down here gives us the same thing as 5 pi over 6? Which is, in radians, pi over 6. And that's our answer. So we get it into that principal value range first, and then inverse sine and sine are going to undo each other. They will. They'll just drop out, because that's what inverses are supposed to do. Alrighty, down here it says, let's use a calculator in radian mode to evaluate these inverse sine values. Okay. So now we're switching to radians. Oh, shoot. Does anybody need to borrow a calculator? We haven't used them in class for a while. Okay, you're good. So mode to radians. And we want the inverse sine of negative 0.81. Negative 0.944. Nope, this is radians. Radians doesn't get a label. If it's degrees, yes, we're going to put our label down. All right, now negative 0.81. That's in the principal value range. Down here a little ways, like so. That would be good. But 3.49 pi. Well, let's see. Let's see if the calculator gives us something good out of this. We want the sine of 3.49 times pi. So sine 3.49 times pi, because we know we always work from innermost parentheses out. So we've got that. And then we're going to take the inverse sine of that answer. Negative 1.539. But this one bothers me because of that 3.49 pi. I would want to take a look at that and investigate that a little bit. All right, so 3.49 pi, we're going to go 2 pi, one more, and then not quite halfway. So there's my angle. So that's not in the PVR. It's not in the principal value range. So I'd have to think, okay, well, how do I get it there? Well, we've got plus, 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 so we know if we need a positive sign, we're going here. And then we have plus, minus, 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 plus, minus, plus, minus. It has to be negative. Well, that means we'd have to place it over here in order to find it. This would be a reference angle. So then we ask ourselves, well, how much? You know, what are we looking for? Well, this was 1, 2, 3 pi, and then we had 0.49 pi more. So that would have given us a negative 0.49 pi. Well, that answer doesn't match this, does it? Let's punch it in and see. Negative 0.49 times pi. Oh, look at that. So whether or not we do it by hand or we use the calculator, we're getting that principal value range. So it's like the calculator knows the principal value range when it goes through to do these. So you'll have not very many, because most of these obviously we want you to be able to do by hand, but you'll have some where you would be able to use the graphing calculator to figure out what they are. Be careful about degrees and radians, everybody. That's going to be the big deal. Inverse cosine. We're done with sine. Sketch the graph of f of x equals the cosine of x. Okay. So we still have our negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi, and all the positives. Well, with cosine, it's Kahala. So cosine high, axis low, axis high. And once again, we have to figure out what is a portion of this graph that would be convenient, that's going to go from negative 1 to 1, but would be 1 to 1. And it's not going to be from negative pi over 2 to pi over 2 this time, because that's going to fail the horizontal line test. But this little chunk right here goes from negative 1 to positive 1. Nancy, do you have a question? Right, principal value range. Yep. So which interval do we choose for this one? This would be a nice one because this is just going from 0 to pi. Just had it backwards in the head for a second. Yep, understandable. So when we had sine, it was always this way. But now with cosine, it's going to go from 0 to pi on the circle. So let's go down here. It says sketch the graph of its inverse. Well, this time when we're switching things around, it's still going to be a negative 1 over 1. It's just that now we're going from 0 to pi. Oh, we don't need any negatives. It's kind of cool. We don't need that. And we can come over here, and we could certainly use the fact that this is square root of 3 over 2, 1/2. Square root of 2 over 2, square root of 2 over 2, 1/2, square root of 3 over 2. And we can graph cosine, because remember, cosine is the x coordinate over there for what we have from 0 to pi. Don't even need to go all the way to pi. Because what we're going to find out is that this is going to look a lot like our squiggly little sign does. Bless you. And if we wanted to put extra points in there, we could. But what we need to know is this. At pi, or negative 1. And we're going to, like I said, do a little squiggly line here right through. Because we know it's a curve. So when we take the inverse, it's also going to be curved at 0 pi over 2. So here, to help you with the visual, we'd see that at 0, we're graphing 1. And so 1, 0 is what we get on here. X's and Y's switch positions. And then here we've got a cosine of 0. So there's our 0 piece. So that's what we have for cosine, which switches those quadrants for us. And that means PVR is from 0 to pi. Principal value range from 0 to pi, so that we can get this to be 1 to 1. So domain and range. Negative 1 to 1 again, and again that's because cosine is adjacent over hypotenuse, so that means we're definitely going to have something that's a fraction between 0 and 1. But now, with cosine, that principal value range is going to change. That's going to be 0 to pi. So sine, cosine. The inverse cosine function is the function f of x equals the inverse cosine of x with a domain from negative 1 to 1 and a principal value range from 0 to pi. This means that x represents a cosine ratio of some positive angle, either acute or obtuse in either quadrants 1 or 2. So my thought is right away, is that going to take care of all the positive and negative cosines? You know, is that going to cover it all? Well, There's our positive cosines. There's our negative cosines. It's going to take care of them. So just by getting that principal value range correct and picking the right portion of the graph to use, we're going to be able to work with all the positive and negative cosines. So like it says, we're looking at quadrants 1 or 2, the inverse cosine function, also again called the arc cosine function, so get used to that, you'll see it every once in a while. But inverse cosine is the angle between 0 and pi, whose cosine is x. Some angle, first and second quadrant, that would give us that. And of course, we want to be able to do some of these without having to grab a calculator, and you might already have these memorized enough where you could do that. So it says find the exact value of the expression without a calculator. And I see cosine, and I think about that principal value range for cosine. And then I think, okay, this has got a negative cosine. Well, that's not here. That's here in quadrant 2. That means there's my reference triangle. And square root of 2 over 2 should immediately put bells and whistles off in our head. Wait a minute, that's that square root of 2 business. That comes from a 45, 45, 90. But how do you get that from this? Well, if you have 1 over the square root of 2, to rationalize the denominator, you'd multiply the top and the bottom by the square root of 2 over 2. Square root of 2 over the square root of 2. And that would give you square root of 2 over 2. So I look at this and think, well, if this is 45, then I've got a 1 here, a negative 1 here, and that would be a square root of 2. Is that going to do it for me? Adjacent over hypotenuse, rationalize the denominator, and you have it. But I can't put 45 degrees down for this one, and I can't put pi over 4 down. Where's this angle at? 3 pi over 4, right, because here's our pi over 4, and this is 1 pi. So there it is. All right, arc cosine of negative 1/2. What triangle is coming to your mind right away? Arc cosine is the same thing as inverse cosine, yeah. It's old school language that we'll see. The 30, 60, 90 has those numbers in it, right? Are we in quadrant 1 or quadrant 2 with the negative arc cosine? Quadrant 2. Okay, cosine adjacent over hypotenuse, bless you. Is that enough for you to find that angle? What does it have to be? 60 degrees. So 60 degrees in terms of radians would give you what? Pi over 3, but it's in second quadrant. So what is it? 2 pi over 3. 2 pi over 3 to get us in second quadrant and have a negative cosine. Alrighty. Looking at C, the first thing that kind of bothers me about it is this negative 1.1 business. But then I look here and I see this is not arc cosine. It's just cosine. So the cosine of negative 1.1, what is that? Well, that's the thing, it's in radians. So we have to think, okay, well, it's negative 1.1. It's not going to make it all the way across to negative 3.14. It won't even make it halfway. It'll be down here at a negative 1.1 radians. That's not in the PBR. So we have to figure out how to get that in the PBR. So negative 1.1 cosine. Well, down here, we're going to have negative, positive, negative. Which one of those stands for cosine? The positive. Sine, cosine, and tangent. So we need to place this angle in the first quadrant. And if you're saying, well, I don't know what the angle is, we do. It's 1.1. Now it's in the PVR. So now if we write inverse cosine of 1.1, inverse cosine and cosine undo each other. They're inverses. They drop right out. But we have to be in the PVR. We have to. So when you see the inverse cosine and cosine, think, okay, this is an easy one. If we're in the PVR, the principal value range, then it's an easy one. Okay, that's too much for a break. Tuesdays, I always do this up with people. Oh, no, a little bit. Our shortened hours, because we still have tangent. So, sine, cosine, tangent. We're right back where we were with sine, which is being from negative pi over 2 to pi over 2, but let's see why. So sketch the graph of tangent of x. Do you remember tangent? Where do we get our asymptotes for tangent? It's been too long. Negative pi over 2 to pi over 2. Do you remember if tangent is increasing or decreasing on that somewhere? Increasing. Looks like this. No problem. That's going to pass the horizontal line test. Why do we really have to take a chunk? Because we don't want to deal with the whole thing. You know, if we put the other pieces on there, then yeah, it's going to fail the horizontal line test. So this is the chunk we want right here. This is the piece that we want to talk about. So what we want to do is say, hey, we're going to go from negative pi over 2 to pi over 2. But we don't want to go forever. So instead, we'll just take this nice middle section right here. That's what we'll do. We'll just take that middle section so that we're working with a one-to-one portion of this. And the graph of this inverse is different because right now we have vertical asymptotes at negative pi over 2 and pi over 2. Remember, they have to switch x's and y's. So now we're going to have asymptotes that are horizontal at negative pi over 2 and pi over 2. And then we know what they do. Asymptotes are things you're supposed to approach, but never quite make it to. So tangent is, it's different. It is. But its principal value range will be right back here. Right back in there with sine. So first and fourth. So with this one, our domain, we can put whatever x's we want in for this. Remember asymptotes, going to approach but never quite cross. Our principal value range on this, that's our negative pi over 2 to pi over 2. But I can't put square brackets on this. How do I know I can't include the negative pi over 2 and the pi over 2? They're asymptotes. It's going to approach it, but it's never quite going to get there. And yeah, this is a good place for us to come back to tomorrow. We'll go after the box tomorrow. And yeah, do whatever. I think you'll be okay with 1 through 21. I think a lot of those were either 36 to 90 or 45, 45, 90. While you're writing it down or take a picture, I'll take a quick peek. I just remember this one going super fast because there wasn't much to it. Oh yeah, they're either special triangles or calculator, so should be able to do those. Good stuff.